5-wire Y system, the parallel neutral conductor is designed to minimize heat generation and reduce our triplen harmonics. The system utilizes three-phase conductors labeled A, B, and C. These conductors carry the main load current. The system also incorporates a parallel neutral conductor labeled N, which provides an additional path for neutral current. This reduces the current flowing through each individual neutral conductor, thereby decreasing heat dissipation. Finally, there is a ground conductor labeled G, which serves as a safety path for fault currents. The fundamental principle behind the 5-wire Y system is that the parallel neutral conductor offers an extra pathway for neutral current. This effectively reduces the amount of current that each neutral conductor has to carry, which in turn lowers the heat generated due to resistive losses in the conductors. Additionally, the presence of the parallel neutral conductor aids in the cancellation of odd triplen harmonics. These harmonics are multiples of the third harmonic frequency and can cause various problems, including overheating of equipment, interference with communication systems, and increased neutral current. By providing a dedicated path for these harmonics to circulate, the parallel neutral helps to mitigate their effect. The applications of a 5-wire Y system with parallel neutral are typically found in commercial and industrial buildings where high currents or significant harmonic content are present. These systems are also beneficial in facilities where minimizing heat generation is a critical concern, such as data centers or hospitals. Furthermore, they are suitable for environments where reducing electromagnetic interference is important, such as research laboratories or broadcast studios. The benefits of implementing a 5-wire Y system with parallel neutral include reduced heat generation in the neutral conductors, which can lead to energy savings and increased equipment lifespan. It also allows for the cancellation of odd triplen harmonics, which improves power quality and reduces the risk of equipment malfunction. This improved power quality also enhances the overall safety of the electrical system by reducing the potential for overheating and electrical fires. Some key notes to consider are that the 5-wire Y system is primarily used with three-phase transformers. The parallel neutral conductor should be sized appropriately based on the specific load requirements of the system. A ground conductor plays a crucial role in providing a safe path for fault currents, ensuring the protection of personnel and equipment. It's important to note that the described system is typically represented as a balanced system. However, in real-world scenarios, unbalanced systems are common. In unbalanced systems, the neutral current may not be evenly distributed between the two neutral conductors. It is also important to understand the role of grounding in electrical systems. Grounding provides a low-impedance path for fault currents to flow back to the source, which allows overcurrent protection devices, such as circuit breakers and fuses, to quickly trip and de-energize the circuit. This helps to prevent electrical shock hazards and equipment damage. There are several different types of grounding systems, including the grounded Y system, the ungrounded delta system, and the high-resistance grounded system. Each type of system has its own advantages and disadvantages, and the best type of system for a particular application will depend on the specific requirements of the installation. When working with electrical systems, it is essential to follow all applicable electrical codes and standards, such as the National Electrical Code, or NEC. The NEC provides detailed requirements for the installation and maintenance of electrical systems, including grounding and bonding requirements. Following these requirements will help to ensure the safety and reliability of the electrical system. Some of the key NEC articles related to grounding include Article 250, which covers grounding and bonding, and Article 300.5, which covers underground installations. These articles provide specific requirements for the size and type of grounding conductors, as well as the methods for connecting grounding electrodes. It is also important to understand the concept of bonding, which is the process of connecting all metal parts of an electrical system together to create a low-impedance path for fault current. Bonding helps to equalize the voltage potential between different metal parts, which reduces the risk of electrical shock. The NEC provides specific requirements for bonding, including the size and type of bonding conductors, as well as the methods for connecting bonding jumpers. In addition to the NEC, there are other industry standards and best practices related to grounding and bonding. For example, the IEE provides standards for grounding and bonding in industrial and commercial power systems. These standards provide more detailed guidance on how to design and install effective grounding and bonding systems. When designing a 5-wire Y system with parallel neutral, it is important to carefully consider the size and type of conductors used for the neutral conductors. The neutral conductors must be sized large enough to carry the expected neutral current without overheating. The NEC provides tables that specify the allowable ampacity of different types of conductors based on their size, insulation type, and installation conditions. For example, NEC Table 310.15b16 provides ampacity ratings for conductors rated 0 to 2000 volts. The neutral conductor should also be properly insulated to prevent electrical shock hazards. The insulation rating of the neutral conductors should be equal to or greater than the voltage rating of the phase conductors. In addition to sizing and insulation, it is also important to consider the material of the neutral conductors. Copper is the most common material used for electrical conductors due to its high conductivity and corrosion resistance. However, aluminum conductors are also used in some applications, particularly for larger conductors. When using aluminum conductors, it is important to use connectors and terminations that are specifically designed for use with aluminum to prevent corrosion and loosening of connections. Another important consideration when designing a 5-wire Y system with parallel neutral is the location of the neutral conductors. The neutral conductors should be run in close proximity to the phase conductors to minimize the impedance of the neutral circuit. This helps to ensure that the neutral current is evenly distributed between the two neutral conductors and that the voltage drop on the neutral conductors is minimized. The NEC requires that neutral conductors be run in the same raceway or cable as the phase conductors. This helps to ensure that the neutral conductors are properly protected and that the impedance of the neutral circuit is minimized. In addition to the neutral conductors, it is also important to properly size and install the ground conductor. The ground conductor should be sized according to the requirements of the NEC and should be connected to a grounding electrode system that meets the requirements of Article 250 of the NEC. The grounding electrode system should consist of one or more grounding electrodes, such as ground rods, ground plates, or underground water pipes. The grounding electrode system should be located as close as possible to the service entrance and should be properly bonded to the building's metal frame and other metal parts. When installing a 5-wire Y system with parallel neutral, it is important to follow all applicable electrical codes and standards and to use qualified electrical contractors. The installation should be inspected by a qualified electrical inspector to ensure that it meets all applicable requirements and that it is safe and reliable. The 5-wire Y system with parallel neutral is a specialized electrical system that requires careful design and installation. By understanding the principles of operation and the applicable codes and standards, it is possible to design and install a safe and reliable system that provides improved power quality and reduced heat generation. When dealing with harmonic currents, it's essential to understand their effects on electrical equipment and systems. Harmonic currents are sinusoidal currents with frequencies that are integer multiples of the fundamental frequency, typically 60 Hz in North America. Odd harmonics, such as the 3rd, 5th, and 7th harmonics, are particularly problematic because they do not cancel out in three-phase systems and can lead to increased neutral current, transformer overheating, and voltage distortion. The 3rd harmonic, also known as the triplen harmonic, is the most common and significant harmonic current. It is produced by nonlinear loads such as electronic devices, computers, and fluorescent lighting. The presence of triplen harmonics can cause the neutral current to exceed the phase current, which can overload the neutral conductor and lead to overheating. Transformers are also susceptible to overheating due to harmonic currents. Harmonic currents cause increased core losses and winding losses, which can significantly reduce the transformer's lifespan. To mitigate the effects of harmonic currents, several techniques can be employed. One common technique is to use harmonic filters, which are designed to block specific harmonic frequencies. Harmonic filters typically consist of a series of inductors and capacitors that are tuned to resonate at the harmonic frequency. Another technique is to use harmonic mitigating transformers, which are designed to reduce the harmonic currents that are reflected back into the power system. These transformers typically have a special winding configuration that helps to cancel out the harmonic currents. In addition to harmonic filters and harmonic mitigating transformers, proper grounding and bonding practices are essential for mitigating the effects of harmonic currents. A well-designed grounding system provides a low impedance path for harmonic currents to flow back to the source, which helps to reduce voltage distortion and prevent equipment damage. The NEC provides specific requirements for grounding and bonding in harmonic environments. These requirements include the use of larger grounding conductors and the installation of additional grounding electrodes. Another important aspect of dealing with harmonic currents is to properly size the neutral conductor. The neutral conductor should be sized large enough to carry the expected neutral current, including the harmonic currents. The NEC provides guidelines for sizing the neutral conductor in harmonic environments. These guidelines take into account the percentage of nonlinear loads in the system and the expected harmonic current content. In some cases, it may be necessary to install a dedicated neutral conductor for each phase to minimize the neutral current. The use of active harmonic filters is also becoming increasingly popular. Active harmonic filters use electronic components to actively cancel out the harmonic currents. These filters can be very effective at reducing harmonic distortion and improving power quality. However, they are typically more expensive than passive harmonic filters. When selecting a harmonic mitigation technique, it is important to consider the specific characteristics of the load in the power system. A harmonic analysis should be performed to determine the harmonic content of the current and voltage. This analysis will help to determine the most effective harmonic mitigation technique. It is also important to consider the cost and complexity of the different harmonic mitigation techniques. Some techniques may be more cost-effective than others, depending on the specific application. In addition to the above techniques, it is also important to reduce the amount of harmonic current that is generated in the first place. This can be accomplished by using harmonic reducing equipment, such as harmonic reducing lighting ballasts and harmonic reducing power supplies. These devices are designed to minimize the harmonic currents that they generate. The implementation of a 5-wire Y system with parallel neutral provides a robust solution for managing harmonic currents, particularly on triplens, and reducing heat generation in commercial and industrial settings. It requires a comprehensive understanding of electrical codes, grounding principles, and harmonic mitigation techniques to ensure a safe, reliable, and efficient electrical system.